The electrode? Mig? Positive, right? So which is the anode, the electrode or the plate? The electrode. Which has more fault voltage associated with it, the anode or the cathode?
Anode.
The cathode has a high, it depends. Thermionic cathode in TIG is low, it's more or less 1 volt. But in MIG, it's about 14 volts for the cathode in MIG and about 5 volts for the anode in MIG. So cathode has more, right? And we already remember then that this cathode fault voltage times the current in MIG, right? Cathode is the plate, gives us more or less the penetration, give or take, right? And the anode fault voltage times the current gives us the melting rate of the wire, give or take, right? So, for example, if we were to flip the polarity in MIG, right now the anode that was having 5 volts more or less, now is 14 volts. Do I melt more wire or less wire? A lot more wire, right? So those are the type of things we discussed intuitively. Would I have more penetration or less penetration if I flip the polarity in MIG? Less, right? Because I go from a 14 volt full voltage to a 5 volt full voltage. Would I have more or less dilution? Do you remember what dilution was? Would I have more or less dilution if I flip the polarity in MIG?
Less dilution.
Less dilution, right? That's good for overlays. All those things we didn't invent, but we are explaining. And what matters for this is that these type of things we're discussing are things that only the most advanced experts know, and you, right? And you know it because you know these few fundamental things. And for you, my hope is all this would be like that. It's true. Right? You don't know how we measure these fault voltages because that's deep research. But I'm giving you a number, which is ballpark. All right, all these things you already know. What I intend to do is now let's take them seriously, beyond intuition. So let's talk about voltage in arc welding. And I'm going to talk about the wire-based processes first, but the same would apply for stick or for TIG. I have not done those in details, but you would know how to extend these yourself. And maybe, I don't know, if you're interested, we can discuss because I can always make the class notes better. So we're going to be focusing on wire-based processes, but there are many. It's MIG, metal core, flux core, sub-arc, right? A lot of things. And the voltages, so far we had talked about 3, right? Before I get into the voltages. Do you remember this drawing we already discussed? Here is the electrode extension or stick out, right? This is what we call the contact tip to workpiece distance. And by the way, just handling this terminology puts you in an amazing place because people get them mixed up. But it's not the same to talk about this length from the contact tip to the plate than this length from the contact tip to the end of the electrode. Right? It's very not the same because the implications for the position rate, productivity, voltage are very, very different. We already talked about anode fault, cathode fault, the arc column. I want to bring now into this thinking that we have is the voltage loss in the leads, right? Like arc welding is an electric process, right? And we need these cables. These cables have some amount of resistance. I want to discuss that. Now, at the contact tip, and I'll get into more of this in detail, we have a sliding contact. We have this copper contact tip. Did you guys take a look when you were grabbing the torch? Did you see the contact tip? We're going to go back to the lab for doing an NDT session. But if you want, or anytime you want, come to a lab and you're going to see it, right? It's a copper contact tip, and the wire just feeds through it, and they slide past each other, right? And because of that type of contact, there is a resistance associated with that, which is not all that small compared with other resistances. So at the contact tip, we have a voltage loss. And also, here, as the current is coming through the wire, we have also another voltage loss because of the resistance at the wire stick out. If I had seen MIG for the first time, I would have said, who cares? But actually matters a lot, right? And that's why I'm taking all this seriously and going step by step. So column, anode, and cathode, this is a slide you have already seen, right? In which you don't need to memorize. Although you need to know what is an anode, what is a cathode. And what I would hope that even if you don't remember the exact number, you would remember that the non-thermionic cathode, like in MIG, has a lot more voltage than the anode, right? And the anode is always an anode, but the cathode depends if it is TIG, if it is MIG or anything else, right? We already saw this, we discussed it, we're good. Let's talk about the leads, right? The cables that take our current to the welding machine. They have two effects. So these notes are already uploaded. The cables have two effects. One is the obvious effect that because it's a long conductor, it's going to have some resistance. We're going to figure out how much that is. Of course, should be large or should be small, the resistance of the leads? Should be small, right? You don't want to be losing power in the leads. Let's discuss those. That's easy to make sense of. The other is that is much less intuitive, and some of you might have had some electrical exposure, right? So is something called impedance or reactance. Have you heard that term before? If you buy speakers, right? The speakers say like 4 ohms or 8 ohms, impedance. Have you seen that? They don't say resistance, they say impedance. Do you know why? So I'm going to get into that. But before I get into this seriously, I'm going to be waving my hands because you didn't have much exposure to electrical concepts. The concept of resistance is relatively simple. Current wants to move and is opposed by something. It's like putting the, like trying to flow a fluid through a porous medium, right? It just doesn't really want to go. That's resistance. Impedance is a concept similar to inertia, right? So imagine I were to have a huge steel ball right here, right? It might have very little to no friction, right? So it would have little resistance, but it would have lots of inertia, right? If I want to push it, even if it is perfectly lubricated and there's no resistance to it, there's all this inertia that it would take me a while to start moving it, right? You follow me? Okay, the same thing happens in electricity. That is called, instead of being a big mass you get to see with your eyes, right? That is what is called inductance, right? Inductance opposes the change in current. So if I were to have this huge steel ball and I want to push, if I want to, if it is static, right? I want to push it, it's going to be difficult. And let's say I push and push and it starts to go farther, faster and faster. Okay, now try to stop it. It doesn't want to stop all that easy, right? You better make way or figure out how to stop it because of inertia. The same happens with current. So the bigger the inductance or the bigger the reactance, there are similar terms I'll discuss, but the bigger this aspect that is related to magnetic fields, is like having a bigger and bigger ball. The more it's going to oppose changing in the current. Okay, so far I'm waving my hands. I'll get into some numbers soon. If I have DC, constant current, do I need to worry about the reactance or the inductance or the impedance? No, because I'm not changing, right? It's all good. If the ball is moving fast or slow, I don't care. It's just going. Now, if I have a waveform, yes, right? So this is an interesting concept. So resistance in the leads, it's a problem always. But this reactance or this inductance is going to be a problem only when I have trying to change the current in my welding machine. For that reason, and I'm still waving my hand, for that reason, when you want to use things like STT, which you all know very well, or any other type of pulsing, as we discussed last class, you want to have short leads. Because if you have big leads, you start have more and more and more inductance, and that starts opposing at your machine trying to change the current. All right. So enough of waving hands for now. I want to give you a few numbers so you have a sense. All right? Okay, for the leads. These two things combined that oppose, that's called impedance. I just want you to know, and you know the word impedance because it's what it says in the back of your speakers, 4 or 8 ohms of impedance. An impedance has two components. You don't need to worry about this. I want to share this with you so you just have. R is the resistance, which you're already familiar with. We'll get more in. X is called the reactance. Has the same units as resistance, except when you do the mathematics of electrical engineering, that's a complex number. And they call the complex variable J because I is already taken by a current, right? We're not going to be using this, but you need to know that for welding, the current from the machine has a thing that opposes it. That's impedance. Impedance has two components. One of those is resistance. The other is called reactance, right? That is more or less a resistance, but a resistance to changing the current. All right, so I'm going to focus only on the R of resistance. This is a formula. It will be on this formula sheet, but really so intuitive that I think you should know by heart. You will have it in the formula sheet, but you should know it by heart. That is, resistance is proportional to the length of the conductor, whether it's a cable, whether it's my electrode stick out, or whatever else might be. And it's inversely proportional, as you can imagine, to the cross-sectional area. More area, less resistance. You knew that, right? So, and this constant of proportionality is the resistivity, right? That is a material property. So whether I have a wire of, if I have a copper wire that is like 1 centimeter in diameter or 10 centimeters in diameter, the resistivity is the same because it's a material property. And it's tabulated in many databases, but you don't care about the resistivity. You care about the resistance because you have a cable. You're not talking about the properties of copper. So you multiply by the length, divide by the area. I put here neglecting skin effect. Again, I'm going to wave my hands here. But if you have a variable, an AC, or if you have a pulse current, like the high frequencies tend to travel on the surface of the wire for those things of electromagnetics, right? So if you have DC, all the cable is carrying more or less the same current. But if you have high frequencies, the current travels on the surface of the wire, such that in reality your resistance is higher because you're not using the whole wire. I'm going to forget about that for now, okay? I'm going to forget about this. It's called skin effect. Resistivity, which is a material property, is often captured with a formula like this that says resistivity at 20 degrees times some sort of variation with temperature, right? Typically, with higher temperatures, you have a higher resistivity, right? And this is for copper. And I put copper here because our leads are made out of copper, and that's what we're talking about. I have these values here. So let's talk about an example in concrete. And you have all this in your notes. So I'm going to be flying over this. But I very highly recommend that when you go home, or when you prepare for the exam, the night before, whatever it is, you go over this, writing it with your own hand in paper. So let's say 400 amps, 60% duty cycle. 60% duty cycle, this means the welder is welding for 60% of the time, and 40% of the time is grinding or taking a bathroom break, whatever it is, right? But typically grinding and matters. So if you are 50 feet away, which is actually a very long lead, 50 feet away is quite a long lead, right? 50 feet away means 50 to go, 50 to come back. So it's 100 meters of leads, 100 feet of leads, right? Are you with me or you're not with me? Okay, no, okay. So I'm the welder. Okay, this is my welding machine. I'm going to weld that table, right? So let's say, for the sake of this example, let's say, and let's use feet because of round number. Let's say the distance between here and here is 50 feet, all right? I'm welding the table, but this is my welding machine. What is the length of my leads in total? It's 100 feet, right? 50 to go, and then 50 to come back, right? The electricity has to come back to the welding machine, right? So if we do it in meters, right? If the total length of leads is 31 meters, this means 15 and a half to come here, other 15 and a half to come back, right? Those are the cable. In our lab, the cables are long, but we roll them up, right? Because nobody gives you cables this short. But in industry, for example, when you're making buildings, you don't want the welder, hey, Joe, go to floor 24 and start welding, right? The guy doesn't want to take the welding machine. So typically they have the welding machine somewhere. It's not in floor 1, right? But then they move all over the building. They use very big leads. If they use very big leads, do you think they can use good waveforms? No. And it's all consistent. Do you remember what they would use to make buildings? What process they typically use? Either stick or flux core, but they don't use processes like MIG with gas. Neither stick or flux core typically use pulsing or waveforms. It's all consistent, right? You see how the whole thing, why things are what they are. But it's good that you know, because if you go to work at Supreme Steel, and all of a sudden you have to start, somebody tries to sell you a super sophisticated waveform machine, maybe it's good, but you better know that you're carrying the machine floor by floor, right? Those type of things. Okay, and so I uploaded for you a lot of material that is super cool about how to select the leads for welding. Right? You have everything, and you have like the American gauge, all kind of things there. So if you look at that material I uploaded, it says in this case, you should use this 2O conductor. It's all explained in there, that has this cross-sectional area. So what is the resistance, voltage loss, and power loss in these leads if they are running at 30 C? Right? Okay. So rho at 20 is 1.724. It's there. The 1 plus this variation with temperature, and it gives me 8.2 milliohms, right? 8.2 milliohms. Of course, it's a small resistance. Huh? It's a small resistance. Okay, at 400 amps, that's 3.3 volts. That's not small. That's not small. That's huge. Actually, of course, your normal welding voltages would be 25, 30 volts. But if you look at the power, that's 1.3 kilowatts wasted in the leads. So if you're welding in winter, everybody wants to be close to the cables. but this is what is recommended. I need to now double check with my friends in industry, because that sounds like pretty crazy. Now you can say, okay, let's use bigger wires. Yeah, but you're going to be paying a lot of money for the bigger wires, the thicker wires. Are you saving us much money in electricity? Well, it depends on the carbon tax, I guess, right? Like, so this is something to start thinking. Okay, I'm going to skip for the impedance, right? The impedance is, remember when I said here, resistance and then imaginary component, this is the reactance, right? The reactance has units of ohms. And the reactance comes from something called impedance. It's frequency times impedance. These things have physical meaning. But let's not worry about that. Let's keep in mind just the formula, right? Frequency 2 pi frequency times the inductance, right? In this case, L is inductance. L is inductance. I know I'm recycling L as length in other aspects, but here L is inductance. Inductance has two components too. One is related to skin effect, which comes from this graph, and I know it's very small. So I'm going to do all of us a favor and skip about the skin effect, right? But we still have the inductance from the length of the lead. And this is kind of funny. Remember, I mentioned a conductor generates a magnetic field according to this rule. If the current flows this way, we generate this magnetic field around. So this magnetic field that is created creates a very weak inductance, but it's not zero, and it matters. Right? If you want a big inductance, you make a coil, right? If you ever open an old transistor radio or something like that, you get to see coils, right? Well, those coils are all about the impedance, right? So this L, like this impedance here, you can calculate for a wire with this formula here, right? And what this formula says is, remember this mu naught? Anybody remembers what this mu naught is? Say?
Magnetic permeability.
Yeah, of vacuum, right? Magnetic permeability of vacuum. Right? When you do a coil, if you ever saw a coil, they put like a nucleus there. That is to change the mu to something higher, so it would have even more inductance. In our case, let's assume it's vacuum, right? L is the length of the lead. And D here is the diameter of the conductor, right? And so for the same example we were looking for, let's consider what the reactance would be for different frequencies. So this one that is due to the skin effect, we said let's forget about that. But this other one, we plug and check into this formula. And it gives us this inductance of in microhenries. Those are the units, right? Let's not worry about that. This Henry times the frequency is going to give us ohms. But now, if we do this 2 pi times frequency times the inductance, right? We get a reactance of 0.034 milliohms at 100 hertz. And 3.32 ohms at 10,000 hertz, 10 kilohertz, right? Question to you, is this big or is this small? Do you remember what it was, the resistance of the leads? Do you remember? It was 8 milliohms. The resistance of the leads was 8 milliohms. And we're saying even at 100 hertz, 100 hertz is a low frequency, right? Even at 100 hertz, we have 34 milliohms. Right? So what would be the reactance at 0 hertz? What is the reactance at 0 hertz? Say? 0, right? 0. Because the reactance is impedance, whatever it is, times frequency, and frequency is 0. So, okay, so what we get to see, what we learn here, is that in this example we have, if we were to have sophisticated waveforms, it's not going to work. Because we're killing them, we're blocking them. Right? So that is an interesting thing. Okay, let's go here. So, and this is for you to know and see how things go. We said that the higher the frequency, the higher the resistance to passing these waveforms, right? Now, again, isn't that funny? You take a welding class thinking that you don't need to know even how to learn and to read and write. But do you remember Fourier analysis? You have to. It has to have been a traumatic memory. Do you remember Fourier analysis? Okay. So in Fourier analysis, it says you can take a waveform and you expand it in sine and cosines, right? Okay, we're not going to be doing Fourier analysis, but you know that. So a welding waveform like STT, you can expand in sines and cosines. And if you remember the Fourier series, some of those sines had low frequency and some had very, very high. So what is happening in the leads is the high frequency ones get killed first, right? So we start to round off our waveforms. And in this example I have here, I have this animation in which, for example, imagine you have a square waveform. Right? The square waveform requires all these that are called harmonics. Right? If we have, I'm going to do it again. It's going to start with the lowest of harmonics, one sine, and then it's going to be 2 sines and 3 sines and everything. Look, this is one sine. Now 2, 3, 4, 5, like it gets bigger and bigger. And that's how you form this square waveform. But you need to have very high frequencies to have this kind of sharpness. And at those very high frequencies, the leads kill it, right? And in the end, for example, I might have wanted to have a sharp square waveform, right? What would be a good use of a sharp square waveform? What would be a reason to have a sharp square waveform? Pulsing. And why not pulsing with a sine waveform?
You just want the sharp rise.
Why?
To get the droplet to detach.
So that is true. Sometimes you want that. And also imagine you have an AC system. If you have a square waveform, it goes from, I don't know, minus 30 volts to plus 30 volts, or minus 200 amps to 200 amps very quickly, passing through 0 very quickly. If you have a sine, it goes gently and passes through 0 gently. Well, if you pass through 0 gently, the arc might decide, OK, I'm done. And that's the whole story between 6010 and 6011. Right? 6010, you can use, works only on DC machines. 6011 is more stable, works on AC, right? Now, you start to see how things go, right? Like, OK, now, if you are going to use 6011 in an AC machine, you'd be running at 60 hertz, right? It's not such a big deal there from the point of view of the leads. All right. That's about the leads. 2 components for the leads, right? One is real resistance. One thing that is important. Resistance dissipates heat. Reactance does not dissipate heat. Reactance opposes your current, but without wasting energy. If we go back to the example of our ball, if there is friction, and I'm pushing something with friction, like this chair, I'm generating heat right at the legs, right? But if I have a ball that is rolling, all my energy is preserved in form of kinetic energy. Nothing got wasted. If you want to stop it, you have to suck up that energy. But if I push this chair like this, the energy went away. Nothing got accumulated. So reactance does not consume electricity. OK. So contact tip, right? So we go from the leads, get to the contact tip. The contact tip has to give the current to the electrode stick out. And it's more or less 2 milliamps. Right? Next year, I'm going to have a better number because we did lots of measurements this year. But I need to process them and make sure I got them right. But it's more or less 2 milliamps, more or less. Right? So, so if you think at 200 amps, right, 200 amps times 2 milliamps would give me 0.4 volts in the stick out. And that times current would give me about 80 watts. So one thing, I want to make sure we have, these 2 formulas will not be in the formula sheet, because you should know them already. Okay, dead. Voltage is current times resistance. Right, and or power is current times voltage. Is everybody familiar with this? Okay, will not be in the formula sheet. I'm telling you what goes, and actually it's pretty generous. But this one, no, this is something you have to know. So that's how I go from these 2 milliohms at 200 amps. That's how I get the volts. That's how I get the power. You can even say, right? All right. So this contact tip resistance depends on so many things. But to give you an idea, the surface finish of the electrode has a significant effect. So much so that the companies can sell you electrodes that have the same composition every other electrode has. But their premium is a surface finish to give you a good contact at the contact tip. Isn't that crazy? That's the market differential of some electrodes is not in the alloy, not in anything else, is that. And because of these watts generated here, most of those watts go into the wire. I don't know exactly how many. I'm still trying to calculate, but I'm going to assume for now all of them go into the wire. But some also still go to the contact tip. And the contact tip can heat up quite a bit. 50 degrees, that has been measured. All right, so this formula, which will be in your formula sheet, again, it's the same formula as before. Voltage is, this is voltage equals current times resistance, and this is the resistance of the stick out. Length of the stick out divided the area of the stick out times resistivity. Okay, the SO here stands for stick out. The F here stands from something I'm sparing you with, but the resistivity of steel, for example, changes a lot with temperature, a lot. So you go from room temperature at the contact tip to melting temperature at the tip of the electrode. And in there, you have almost an order of magnitude in variation in resistance, right? So which point do you take, right? I already did that type of calculation, and more or less for steels, this would be the value of the effective resistivity, right? It depends on many things, but more or less this is a reasonable number, at least for now in the class. Now, the cross-sectional area is the electrical cross-section. For example, in MIG, what would be if I have a wire of diameter D, what would be the cross-sectional area of that wire? Correct. Who said that? Thank you. Now, if I have flux core of the same diameter, is that the same cross-sectional area for resistivity? No, it's smaller, right? Because now we don't have the core. It just goes around, right? So this voltage depends on the current carrying part. Same with metal core. Although the metallic powders are conductive, they don't really count, right? Because it's powder, full of contact resistance. So what we look for is the cross-sectional of the metallic sheet. Funny enough, they don't publish that. So I've been trying to figure it out myself. I call the companies and they say, you know what, I cannot tell you, go measure it yourself. Big secret, right? Like now we're going to steal the business of the big manufacturers because they give me what this would be. Anyway, you know what that is, even at least in theory. So now we can calculate the voltage of the stick out. Can anybody tell me a typical stick out? Who said 2 millimeters? You 2. But you welded. No, you welded and you welded and you welded. All of you welded. Not 2 millimeters. It's kind of a half an inch. That is 12.7, right? 10 millimeters, something like that. In subarc welding, it's longer. But it's typically half an inch. So if you want a ballpark number, contact tip to workpiece distance is more or less 1 inch, and the stick out is half of that. Of course, it varies so much, but more or less. But 2 millimeters is super close to the contact tip, right? That's too close. But the effective resistivity. Now, another thing, I saw, if you look at a bunch of welds that are, yeah.
So they give you the effective resistivity, but they don't give you the reactance?
Okay, let me tell you something. I give you a resistivity because nobody else does. But so you have the resistivity tabulated. For the reactance, doesn't depend on the material, right? Because it's an electromagnetic thing. I will give you a formula for that, but I already gave you a formula, right? But we can synthesize it more or less right for reactance too. I have a slide later on that. Okay. Right. So if you look at a bunch of like suggested welding parameters, what you're going to get to see is that for MIG, the current density is, you get current divided the cross-sectional area is more or less this number I have here. 2.2 times, so 200, what is that? 220 million amps per square meter, right? 220 amps per square millimeter, right? And this is, I mean, you're going to say, well, for a given wire, I can put any current I want. Yes, in theory, yes, but if you want to put too much current, you're going to go to a thicker wire, right? So by the time, if you account what people tend to do for a given wire, right, or a given current, what wire that you're going to pick, you get that ballpark. This is more or less kind of right? So it's 220 amps per square millimeter, right? So if this number is more or less constant, right, then you can say that the voltage of the stick out, I would multiply this number here by the effective resistivity, and is 0.16 volts per millimeter. Now in inches, and I'm going to call people from industry to confirm this, but this number sounds so round that I'm pretty sure they would be using something similar. It's more or less 4 volts per inch of stick out. So what would be a typical voltage, stick out voltage in reality? 2, right? I said it's half an inch stick out, right? So yeah, sure enough, it's more or less 2. Of course, if you change the current, you're going to change these voltages and everything. I'm giving you like very ballpark values, but I also gave you the formulas to calculate it properly if you want. So as a summary, the arc column, the anode, and the cathode we already discussed. About the leads, I looked at a reasonable current density in the leads. So if you use this current density of that is 6 amps per square millimeter, right? You get more or less 0.1 volts per meter in the leads. So if I were to have a total length of 10 meters in leads, what would be my voltage loss in the leads? 1, right? Like so this is a convenient number, and it's and again, you can say, well, depends on your current. Of course, it depends on the current, but when the current is too large, you move on to the next type of wire and the next type of wire. So this is more or less like a, yeah.
Sorry.
What did I say wrong?
No. I had a question about the stick out voltage.
Yeah.
For stick welding,
Yeah.
you have roughly a fair bit longer stick out, but you have a significantly larger diameter.
Okay, have not done it yet. We can. We have all the tools to do it. And if any of you want to impress me, tell me what happens in stick welding. The resistance of the electrode is more or less the same we have here, the one I gave you, right? But of course, it's a thicker wire and longer. And actually, it gets hot.
Right.
I don't know how much role it plays.
Right. And Dave mentions that everyone in the stick welding demo, the first time I'd heard that, he talks about kind of warming up the electrode. It was easier, he claimed it was easier to start welding if the electrode was warm, which I hadn't heard before, but it seems to be the case. But when they qualify weld procedures, if the voltage changes as you burn down your electrode, which voltage do they use?
Do you have to write the length of the leads?
So is there any, I know that because of the wire we have like, if it was an inductor,
Yeah.
but when we are actually welding, there is one plate and another plate, which
Yeah.
it will be like a capacitor. Is there any model, like a equivalent circuit that can model a weld, like with a capacitor?
There is a capacitance. Okay.
And power source.
So the question is if we should account for some sort of capacitance in welding. Okay, the straight answer is I don't know. But I'll tell you what I'm pretty sure of, that we could check. For some reason, I don't know, electrostatics never appears in welding, very, very seldom, right? And only in the electrode sheaths. But the capacitors that work because of electrostatic charging, I don't think there is any significance to that charging. I don't think so. And pretty much anywhere in the machine, I've never seen capacitance come up. Yeah.
Because the problem with these, well, I didn't knew about this, right? But the problem with these type of machines is when you have a lot of inductance in any industry,
Yeah.
you will have to correct your power factor.
Yes.
So all
Yeah.
these type of problems will arise when you have that. So
Okay, but what you say is like very often when you have electric motors and many types of operations, you have overall your factory ends up being like acting as a big inductance, and that's a problem. So you get charged for that, and there are many problems with that. So companies often have like a big bank of capacitors to offset it. Now, for the most part, welding is all this issue I'm trying to discuss as it affects the act of welding. Overall, the welding machines have very little inductance. So when you plug them on the wall, their inductance is relatively low.
yeah, but like for example, if we were to analyze this with the power factor, like the actual power and the apparent power, to search for the loss of voltage and like all these issues affect the actual welding. That's why I ask if there is like an equivalent circuit, because if we could do that, like analyze that as a circuit, it will kind of be good, because then we will know how much current we're gonna have.
We don't need correction typically. That's what I'm saying. But yes, there are many equivalent circuits, but I don't teach them, and actually, because I don't know them all that well. But the companies have all these equivalent circuits. Welding machines typically have no capacitance. From the point of view of load, their inductance is very low, right? It's not like an electric motor or something like that. Yeah. So the resistance, we talked about resistance of the leads. The reactance part. So let's say the reactance. Remember when we said 31 meter leads, right? Running at 100 amps, at 100 hertz, right? So 30 meter leads running at 100 hertz. So 100 hertz would be 10 to the minus 3, and 31 meters leads, this would be 0.03, right? This would be 30 milliamps in that case, right? And if you remember, that's what we had calculated here, 34 milliamps in this case, right? Doing all the fancy mathematics. So this is just like a rule of thumb. If I don't tell you anything, you can use this, that will be tabulated. And if I ask you to calculate it, you would have the formulas to calculate it. But this is the way of calculating your reactance. Right? You multiply by the length of the lead. This per meter is per meter of leads, right? We're talking about the leads. So if I have 34, let's say 30 milliohms of reactance, and I'm running at 200 amps, right? how much energy, how much power am I dissipating in that reactance?
Can you repeat the question?
I said, if I have 30 milliamps of reactance and 200 amp current, how much power am I dissipating in the reactance? How much power does a reactance dissipate?
The reactance doesn't consume electricity.
Right, reactance doesn't consume electricity. The problem of reactance, right, is that you might increase the voltage of your machine. You might play games aside. But the reactance is not dissipating electricity. It's just destroying your waveforms. That's what it's doing. OK. At the contact tip, we're going to call the resistance of 2 milliohms, right? And at 200 amps, the 2 milliohms. How much power is that? It's 0.4 volts times the 200 amps. That would be 80 watts, right? So, and then the stick out. If we have this current density ballpark that I mentioned, it's like 4 volts per inch, right? And for a half inch stick out, it's 2 volts. Good? All these volts are what you see in the machine panel. You see a voltage, right? And people would think, oh, voltage is voltage. Well, now you know there is so much to voltage than a number, right? OK. So now, look, based on all these things we have discussed, and these formulas here, voltage is current times resistance, power is current time voltage. So let's say 200 amps DC, 12 millimeters stick out. C5 means argon 5% CO2, right? C10 is argon 10% CO2. They call it that way. So at the contact tip, you'd have, right, 200 amps times 2 milliamps, 4.4 volts, 80 watts. The electrode stick out, let's call it more or less 2 volts. We can go fancier if we want, but it's more or less that based on the suggestion I gave you. And that would give us 400 watts. Right at the anode, we have anode fault, 4.8 volts, times the 200 amps, almost a kilowatt. Right? You get to see this is pretty big, but this is not negligible. For this reason, you have machines, actually, in which they call the push. Depending on, well, if you play with the electrode extension, right, you can change this amount of power, right? We'll talk about that. Here, the arc column, if it says 0.8 volts per millimeter times 6 millimeters, would be 4.8. And I'm ballparking it. A third of that goes to the plate. Again, prove me wrong, right? That might change a bit. Cathode fall, almost 14 volts, 2.7 kilowatts, right? Almost 3 kilowatts. That's what gives me penetration. In total, I would have a total voltage of almost 26 volts. All these watts here, of which 640 are lost, because whatever energy I put in the wire, then it comes back into the melt, right? The only thing that really goes wasted is these 640 that are 2/3 of the arc. And this is something that Mitch mentioned on Thursday last week, right? Or Tuesday, when was that?
Tuesday.
Tuesday last week, right? you can start making some sort of an efficiency assessment. We're going to have a whole lecture on efficiencies. But if I put all these 5.16 kilowatts, I lost 640. What goes in is 88% of that. And that's a reasonable efficiency for MIG. Again, lots of people measure it. They don't agree. This number, somebody might say no, and somebody will say yes, which means it's not crazy, right? So this gives you some sort of efficiency for MIG. Now, if we were to have a 5-meter reach, right, for our leads, that means a 10-meter total, right? That would be 0.1 volts per meter of lead. That would be 1 volt. So in total, your machine panel would be reading 27 volts, 26.8 actually, right? Give or take. And these are reasonable numbers. Perfect, I'm not too sure if they are perfect. But these are reasonable. But in addition of being reasonable, we know so much now. We can think in ways others don't. All right. So I want to tell you a couple more things, but how do you feel about this? This is quite an X-ray of like how welding works. This would apply to stick electrode too. I myself have not done all those numbers perfect, but more or less the same numbers would apply, and you would see something similar. All right. So I want to tell you, as we're discussing about this effect of voltage and power, still no equations here, but to get into your intuition. So look at this. If I were to, how does MIG run on constant current or constant voltage? MIG. Constant voltage, right? And so what other thing where does the current, would I affect the current in MIG? If I want to have a higher current in MIG, what do I change? Wire feed speed. So you give more wire feed speed and the current goes up, right? That's the way the machine like sets the current by itself to be whatever current is going to melt all that wire with that arc length. So imagine I increase the voltage, right? And the voltage, if you remember, there is relatively little voltage in the stick out, right? It's about, if we were to have a half-an-inch stick out, we have about 2 volts here. And if we were to have a 6-millimeter arc, right, we have almost 5 volts here. So if we increase the voltage, the arc wins, and the arc gets longer, right, if we increase the voltage. If we increase the voltage, the arc gets longer. Now, what happens to the current in that case? Same wire feed speed. And I increase the voltage. What would happen to current? Oh, higher current. Fine. Why? Why higher current?
Because of the gap.
Say?
Because of the gap.
But what does the gap do for the current? Well, the wire feed speed is the same, so you're melting the same amount. Right. So look, to melt an amount of wire, I needed all this energy. Cathode flow, more or less the same. Anode flow, more or less the same. Right? The arc does not affect the electrode melting. Contact tip to wire, more or less the same. Electrode stick out, shorter. So I'm generating less energy at the electrode stick out. right? So in theory, unless I increase the current, I cannot melt. And I increase the current, and when I increase the current, like everything goes up, but especially I would have more energy deposited at the anode. You follow me? Super, super important. And again, I'm teaching this to you, and I expect you to do this in the exam. But in all fairness, for all the people who have spent like 100 years welding, only very few can make sense out of this. But you are among those. So this is high level. So you increase the voltage, current is going to go up. And this is the reason. Because the machine all of a sudden realizes it needs to give it more juice to keep melting the same amount of wire. If the current went up, you're going to have some higher penetration probably. You're going to have also, because if you remember the arc, I said it's like parabolic, it's going to be a wider arc. This is amazing because now you can start making sense out of things. Right? You can, if you want a weld to be wider, you would increase the voltage, but you know what's happening if you increase the voltage. What happens with the current? All right. Oh, by the way, another interesting thing. I'm melting the same amount of wire. But this is wider, right? So it's going to be flatter. This is super important for things like fatigue performance. Typically, you want a flatter bead more than a crowned bead. Right? Very often people say, oh, we have a crowned bead, blah, blah, blah. You start to get a sense of how the variables play. OK, look, you can accommodate imperfections. For example, something we're working on in the lab, and it seems to be an endless pending job. Imagine you can adjust the torch standoff, right? Imagine you can adjust the torch standoff, for example, with an Arduino, right? And a servo motor. So if all of a sudden your plate is bent, undulated, or something, for whatever reason, the plate that they promise you is perfectly flat. It never is perfectly flat. Now, the plate is taller, and what would happen? Because you keep more or less the same voltage. You told the machine to keep the same voltage. All of a sudden, you have a shorter electrode stick out. Current is higher or lower? It's higher, right? The current is higher. And I can have a sensor for the current, and I can tell the torch, OK, go back up. And the torch goes back up, and everybody's happy. Almost nobody does this. But to do an Arduino that does this is going to take about $100 in hardware, maybe $200 in hardware. Savings is tens of thousands of dollars. So what I hope is that in our lab for sure, but all of us, we're good enough at hacking things, and we have a deep enough understanding. Because we can have a startup in making like basic automation for welding. Let me tell you guys, we're all changing the cars for much better. Right? With this little we know. All right. I'll show you something in which a consultant was paid reasonable money, and it wasn't me, and for solving a problem that was a quite difficult problem. And they were making overlays, and they were having too much dilution. Right? How do you reduce the dilution when you're making overlays?
Less current.
OK, so you can, of course, you can have less current. You would have less penetration, but you melt less wires. So you're more or less where you started. So less current is a no-go.
Less arc length?
Say?
Less arc length?
Less arc length. OK, let's think together. So if we have less arc length, with more or less the same voltage, we would have shorter, sorry, you say less arc length, like you lower the voltage, right? That's what you say? less arc length, you lower the voltage. The current would increase, but you have this narrow track. That's also a problem, yeah.
Increase the wire speed.
Okay, but if you increase the wire feed speed, it increases the current, which increases your dilution, your penetration.
You decrease current, increase voltage.
You have this is a merge arc welding, and it's more or less like MIG. They were running on constant voltage. So if you decrease you can play with the voltage, but you don't touch the current. You touch the wire feed speed. So this is what they did. As you realize, with all you know, you're more or less circling around it. But many people don't even know what you know, so they couldn't even circle around. What they decided to do is to do something that very often people say don't ever touch. They change the torch standoff, right? The contact tip to workpiece distance. Now, if you change the torch standoff, right, you would have the same, for the same voltage, or more or less the same voltage, you would have more or less the same track width, because it matters. For example, when what you suggested lower the voltage, or like lower the arc length. But then you get a narrow track. And if you're making overlays, then you start to make like many more passes. That's also a problem. So they wanted to keep the same width, right? But if you want the same width, you would have more or less the same arc. But if you increase the torch standoff, now you have a higher stick out. And because you have a higher stick out, you're putting more power into your electrode extension. So that allows you to lower the current at the same wire feed speed. Now you can have the same wire feed speed with lower current. And the reason is because of the higher stick out. And the current is lower, then the penetration is lower.
So why is it military, not in no-go area?
Well, what happens is, if it is a knob, you still can have a problem, but a knob is easy to put back in place. But when you go and physically change the hardware in this type of machines, everything's screwed in place. You start fidgeting with that. If you don't like it, it might be very difficult to get back to where you were at the beginning, right? And if you know what you're doing, you take a gamble. But if you don't know what you're doing, you're very, very afraid to rock the boat. And one of the reasons we have this class is because with this amount of knowledge you guys are having, you might be more willing to rock the boat than people who have something that works mysteriously. So for you, there should be far fewer mysteries. Super important because this was very important for the company. They could reduce dilution. Can anybody suggest other approach to reducing dilution?
AC waveform?
All right, Mitch suggests AC waveform. Yeah, and this is right. I would like somebody, not Mitch, to suggest why AC waveform would be good at reducing dilution.
Is the current fluctuate?
It's true, but so what?
You switch between having your plate be a thermionic, non-thermionic cathode, and your wire being an anode.
Right. So if I switch that, what happens? Yes, that's
Overall voltage should be lower
the overall voltage. Why would it change?
because
You're into something, huh? But the overall voltage shouldn't change.
but the overall current should change. Forget why it should change.
Because the cathode, when the electrode is positive, as always, right, the plate is the cathode at more or less 14 volts, 13.8. But when I flip the polarity, it becomes an anode at 4.8. So I melt less. On the other hand, my electrode, right, it goes from being an anode at 4.8 and on occasion being a cathode at 13.8. Right? So actually, for the same wire feed speed, I need to lower the current. Right? Super, super interesting. Now, what's the catch? Well, you need to buy a new machine. And a machine that can do both polarities costs more or less like two machines, one for a positive and one for the negative. It's not quite like that. So what do you want to do? I mean, in this case, the guy is needed to go with a wrench to change it. In the other case, you would move like the AC balance the way you like it. Who are you? The guy who bought a fancy machine or the guy with a wrench? I don't know. But whoever you are, now you know what to do, right? And you can start making your decisions based on this. I think this is pretty cool. This is a real case, huh? Yeah.
What was the first option?
The first option is increase the longer contact tip to workpiece distance standoff.
So lower the current and
Right. If you do that and you keep more or less the same voltage, the current is lower because the electrode stickout is longer. And you have all the energy from joule heating.
does the wire feed speed keep?
The wire feed speed is set. When you do an overlay, right, you move at certain speed and you put so much wire. And they go together. You cannot change them because all of a sudden your deposit is going to be different. Right? We're going to have a session on that too. Please think about this. Yeah.
When you say approximately the same voltage,
Yeah.
is that because if you have a slightly longer wire with the same, approximately the same voltage drop, it's going to change the heating of the wire a little bit?
Well, I say approximately the same voltage because if the arc length in both is the same, this arc is more or less the same voltage. But the electrodes stick out, right? On one hand, the current is slower. On the other hand, the stick out is longer. I need to think for an extra 30 seconds. If they really balanced out, we should. Do they?
Well, I'm thinking if your wire feed speed is the same, the heat input to your electrode, or the heating of your electrode should be about the same, right?
No, because his power goes with the square of the current.
Or the square of the voltage.
Right. Okay. We're going to think about this, but it's more or less the same. What I said, the way I look at this, which is not exact, I tend to think there is close to 0 voltage drop in the stick out. Of course, it's not. I just told, and all the voltage drop happens in the arc. That's the way I look at it. It's not exact, but at least it takes me to the right places. And I also know the formulas to do it right, formulas that you also have. Right? OK, so we have a few more minutes, and I want to get the next topic started. That is, as we discuss about this, right? This is just so amazing. We talked about the plasma arc, and the voltage is associated with it because the non-local thermodynamic equilibrium, whatever it is, right? But that gives us an anode fall, cathode fall. And now you start to see how there's a power associated with different parts of the weld. You started to see also what happens in the leads, how they affect pulsing or not, and if they're long, they're short. All those things, right, are so good. So what I want to do next is let's grab these powers we have that we understand, and let's calculate related to wire feed speed. Because now we are going to be able to understand some things that, again, nobody tells you straight. But all basic engineering principles that help you understand the practical problems of welding. So we have 5 minutes here. So this is the position rate, or some people call it the melt off, some people call it the burn off. This I'm going to be discussing. I care about it because it helps us understand the physics of welding, the mechanisms. But this we're discussing, you know where it typically falls in notes if you look at brochures? In the economics section. Not because they have a love of understanding, but how can you calculate the cost of welding if you don't know how many pounds an hour you're putting? right? So I already uploaded, I don't know, remember which module, one of the ESAB modules on economics of welding, and has much of this. So how many of you took heat transfer with me? 1, 2, 3. I think it's a couple. Okay. So what I'm going to do is an energy balance, right? And if you remember, we always write this equation in the heat transfer class. The heat that comes in minus the heat that goes out plus the heat that is internally generated equals the heat that is stored. And as we discussed in the heat transfer class, you don't write this equation without having a control volume. And here's the control volume. So the control volume is the electrode extension all the way to the droplet. So by Q in is the heat that comes in, out, the heat that comes out through this control volume. Heat generated is what is generated inside. Right? It's heat stored is what is stored in there. Okay, so heat in. What heat comes into the electrode? Is the heat of if in MIG typically it's the anode fall, but could be a cathode fall, right? That's why I put fall. Could be anode, could be cathode, whatever it is on the surface. Then there's energy coming from the arc, which I already told you is close to 0, right? But I'm just writing the things properly. Plus the heat that comes from the contact tip, right? The contact resistance. That's the heat coming in. The heat that goes out is a little bit by radiation, a little bit by convection here. Those are so super, super small. I already calculated them in another case. We can totally forget about those. But there is something which we'll also forget about, but it's not so small. That is evaporation. So remember the welding fumes and all these questions you had in your exams. If everything goes right, and I think we're super on track, Thursday we bring back the exams. So all these questions about how to protect the welder from fumes and all those things. Okay, the fumes come from the evaporation of the metal. And as you know, evaporation takes heat away. That's why you don't go out in winter with your wet hair, right? Because worse than freezing, it's going to start evaporating and it's going to give you really, really, really cold. So this is latent heat of evaporation times the enthalpy of going into evaporation from the starting temperature. And this is more explained later. Heat generated, guess what? Heat generated, we have it here, right? What we discussed. I square R, and resistance is length of the stick out, effective resistivity, and cross-sectional area of the electrode. And what is the heat stored? I mean, isn't welding awesome? We go from Fourier series to electromagnetics. Now, remember thermodynamics, right? Thermodynamics in which you have enthalpy, right? Enthalpy is the amount of heat the material contains. So here we have the flow of wire, the amount of mass of the wire coming in times the enthalpy of the droplet, right, at whatever average droplet temperature the droplet has, minus the starting enthalpy, right? You start with the wire coming at room temperature, and you end up with a wire with a droplet, to give you an idea, about 2500 C. That's hot, right? So this comes from thermal. I suggest we stop here. We're going to pick up on this on Thursday. And in the seminar, we're going to do calculations relating these things. Just as a teaser, the calculations we're going to do are the numbers, the real numbers that appear in catalogs, but from first principles. All right. I'll see you on Thursday. Thank you.